This lecture follows directly from where we left in the previous video. Let's get back to the small mass delta m. This time around, a force F is exerted on delta m, which causes delta m to rotate about a fixed axle at radius r. Notice that F is applied perpendicular to r. How does Newton's second law apply in this case? Well, the object rotates because of the torque, or moment that comes from the force. The force causes the object to accelerate in accordance to Newton's second law, F equal to ma. However, since the force also causes the object to rotate, the acceleration in this context is the tangential acceleration. That is to say, delta m is undergoing circular motion while it is moving faster and faster. Now we can rewrite the equation using angular acceleration instead of tangential acceleration. We then rearrange the equation and cast the final form of the equation in terms of moment of inertia, which we just studied in the last video. We thus have the equivalent to F equal to ma in rotational dynamics. Torque is equal to moment of inertia times angular acceleration, tau equal to I alpha. If we associate tau to force in accordance to tau equal to F times r, remember that equation, and angular acceleration alpha to tangential acceleration a equal to alpha times r, then we can associate moment of inertia I to inertial mass m. Indeed, both carry similar physical meaning. While mass refers to the translational inertia of an object under the influence of force, moment of inertia refers to the rotational inertia of an object under the influence of torque. We went through this in the last lecture video. Okay, let's say delta m is now rotating about the axle. Whether it is accelerating or not, delta m for sure carries kinetic energy. We have established earlier in lecture 6 that kinetic energy is possessed by any moving object, and it is given by 1/2 mv square. Of course, in this context, phi refers to the tangential speed of the object. We can then recast the equation in terms of angular speed omega. We rearrange the terms and replace mr squared by moment of inertia. We will arrive at the final form of the kinetic energy of an object rotating about an axis, 1/2 I omega square. This kinetic energy, which is associated to the rotational or circular motion of the object, is called rotational kinetic energy. And guess what? Notice the similarity between the so-called translational kinetic energy equation, 1/2 mv square, and the rotational kinetic energy, 1/2 I omega square. Notice how the moment of inertia I is once again associated to the initial mass m, and the angular speed omega to the tangential speed phi. Both even carry the same factor 1/2. Kinetic energy and momentum come hand in hand. Any moving object possesses kinetic energy as well as momentum by definition. I guess by now you should have been able to guess where this discussion is going. We would like to find out the equation that describes the momentum of the object associated to its rotational motion. It is called angular momentum. It is typically denoted using capital letter L, and it is related to the tangential momentum P by the radius r. L equal to r times P. Similar to the previous procedure, we can recast this equation in terms of angular motion terms, some rearrangements, and we have another way of mathematically describing angular momentum, this time around in the form of moment of inertia and angular speed. And guys, once again, angular momentum shows a remarkable similarity to its tangential or translational counterpart. I is associated to m, omega is associated to phi. If by now you still do not get it, let me put everything down explicitly in this table. You might have complained to me on the sheer number of equations you need to study for the exam. But look at this table. Do you recognize any pattern here? First, how the tangential quantities are related to the angular quantities via r. After all, r is what distinguishes the two types of motion. Angular motion exists because the object moves at fixed distance from a reference point. That reference point is what we call center of rotation. The fixed distance is what we call radius. Second, this one-to-one relationship between tangential and angular quantities result in many of the dynamics equations having the same pattern. If you remember the Newton's second law F equal to ma equation, I'm 100% confident you all remember that equation. You can easily recall the Newton's second law in rotational dynamics, tau equal to I alpha. What you need to remember is that F is related to tau, m to I, and a to alpha. Same thing can be said for rotational kinetic energy and angular momentum equation. This is an obvious example that in physics, though you may think of it as a hard and complicated subject, there is order, there is simplicity. We should study physics by looking for and following this order. Got that? But wait a minute. What we have discussed so far is only a small mass delta m rotating about an axis at radius r. How about a large massive rigid body? Are the equations in the previous slide still applicable? Do we need to modify the equations? Well, fortunately we do not need to. The equations that describe the dynamics of any rigid body, regardless of mass, shape and size, are the same. We use the subscript body to remind ourselves that these are the equations pertaining to the whole rigid body, instead of individual small masses delta m. The reason why the equations are still the same is because although each delta m that encompasses the rigid body moves at different tangential velocity, they all share the same angular motion. If this guy rotates by say 20 degrees, that guy will also rotate by 20 degrees. Of course that will mean that that guy will have to move at higher tangential speed than this guy, but both still move by 20 degrees as far as angular displacement is concerned, and that implies all delta m will share the same angular velocity and angular acceleration as well. If we look at the equation for torque, for instance, the total torque of the rigid body is given by the sum of the torque of individual delta m. But since all delta m share the same angular acceleration, what is left to do is to sum all the individual moment of inertia. We just learned exactly how to do that in the last video. Thus, going from equation for describing the rotational dynamics of individual mass delta m to those describing the rotational dynamics of a rigid body is as simple as replacing the delta mr square by the moment of inertia of the rigid body. For basic shape rigid bodies such as solid sphere, solid cylinder, etc., you may need to refer to the table shown in the last video.